Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Hello, good morning. Welcome to Pastor Victor's Academy. I'm glad you are here, and I'm sure that you'll be learning a lot from this video. So please do to pay attention as we go on. In my last video, we looked at basic concepts and definitions, and also we looked at pressure, specific volume, temperature. So in this video, we'll be looking at energy, work, and heat. So the first one is energy. What is energy? This is the capacity of a system to perform work or transfer heat. It is a fundamental property that appears in different forms. So energy can appear in different forms. It does not have only one form. In physics, we usually define energy as the ability to do work, but in thermodynamics, energy is the capacity of a system to perform work or transfer heat. So when a system is capable of performing work or transferring heat, we say the system has energy. So we are going to be looking at energy in different forms. The first one is kinetic energy. This is the energy a body or system possesses because of its motion. So if motion is not involved, we won't be talking about this form of energy. So the energy a body or a system possesses because of its motion is known as kinetic energy. Here we have Ke is equal to half mv squared. Now what is mass? What is v? Velocity. So Ke is equal to half mv squared. Now the next one is potential energy. This is the energy a body or system possesses due to its elevation or position relative to a reference level. So is energy a system has because of its elevation or position with respect to a reference point. It is important to note that without a reference level, there is no way of measuring potential energy. So it's important you take note of that. If we don't have a reference, then there is no way talking about what potential energy, because it's usually with respect to a reference point. We have PE equal to mgz, where m is the mass of the body, g is acceleration due to gravity, and z is the height above the reference point. Now the other one is internal energy. It is the sum of all forms of energy contained in the random motion and interactions of molecules, atoms, and particles that make up the system. In other words, it is the energy stored within a system at the microscopic or molecular level. So all other forms of energy stored within the system at the microscopic level is called what? Internal energy. So the symbol of this energy is U. So here is the symbol U for internal energy. For example, internal energy increases or decreases during phase change. So when a system is moving from one phase to another, let's say from solid to liquid or from liquid to gaseous phase, the temperature of the system does not increase or decrease, it's constant. So what happens to the system at that point? The internal energy is what? Increasing. The particles of the system, they can now move freely. They possess more energy because the heat you are supplying to that system is going to somewhere. You get, it's going to somewhere. So that heat is giving the molecules more energy to move what? Randomly, even though it does not show in the temperature or in the movement of the entire system. That's why it's called internal energy. So in the case of kinetic energy, the whole system is moving, not the particles. Instead, the system is moving. Then in case of potential energy, the whole system is placed at a certain height with respect to a reference point. But for internal energy, the molecules of the system are moving or changing position, but not the entire world system. The system could be in the same place, but the molecules are moving or changing position. So we'll talk about the next thing, that's work. This is the energy transfer across the boundary of a system that occurs due to a force acting through a distance and not due to a temperature difference. So in thermodynamics, energy can be transferred through work or heat. Now, in the case of work, it occurs due to force acting through a distance, which means that when a force acts through a distance, energy is transferred. And that form of transfer is called what? Work. Note, work is not a property. Unlike energy, unlike pressure, unlike specific volume, unlike volume, and unlike temperature, work is not a property. Instead, it is a path function, and that means it depends on how the process occurs, not just the end states. Now, take for instance, we have state 1, state 2, and the system can arrive at state 2 through this part, or this part. Now, work does not depend on the states. Energy will depend on the states because energy is what? A property. It doesn't depend on the parts. But in the case of work, it depends on the word part. So if you're asked to calculate work done by a system or on a system, you'll be looking at the path the system followed to arrive at the next state. So if I follow this path, follow this path, follow this path, I will not be getting the same value for work. Now, following this path, I may be getting 10 joules. Following this path, I may be getting what? 8 joules. Following this path, I may be getting 11 joules. So when you're asked to calculate work, the first question you ask yourself is which path was followed? So you calculate work with respect to the path what followed to arrive at the next state. Another thing to note is that work and heat are the only two modes of energy transfer across a system boundary. So energy will be transferred across the boundary of a system either as work or as what? Heat. Then again, work is always defined from the system's point of view. What that means is that work done by the system is considered to be positive. Work done by the system is considered to be what? Positive. Then work done on the system is what? Is negative. So generally, work is equal to integral V1 V2 P dV. Here, P is the pressure of the system and V is the volume of the system. So V1 refers to initial volume, V2 refers to what? Final volume. dV here is elemental volume. So before we begin to use this formula, it's necessary we first of all define what? Our pressure. Of course, in physics, we are familiar with the formula work is equal to force times distance. But in thermodynamics, we are looking at work in terms of what? Pressure. Now look at it. Pressure is equal to force per unit area. Then force is equal to PA. So when we replace F with PA, we'll be having work is equal to PA times what? Distance. Remember that area times distance is equal to volume. So work is equal to what? PV. So remember that we'll be dealing with changes in volume. So a better way to represent this would be to use the integral what? Form of it, where we'll have integral of P dV, that's from V1 to V2, is equal to what? Work done. Now I want to define work for some special cases in thermodynamics. And the first one we have is the polytropic process. So in this case, PV to the power n is equal to C. P is pressure, V is volume, N is index, then C here means constant. In other words, PV to the power N is constant. So we have in P1 V1 to the power N is equal to P2 V2 to the power N equal to P3 V3 to the power N equal to constant. Now remember that work is equal to integral of P dV from V1 to what? V2. So we'll be defining P using this formula. P would be C over V to the power N. Now substitute for P here. We're having work is equal to integral V1 V2 C over V to the power N dV. Now this thing is the same thing as integral V1 V2 CV to the power minus N dV. Now we can bring our C out. We'll be having work equal to C V1 V2 V to the power minus N dV. Now the next job would be to get the and multiply it by what? C. Now remember that integral of x to the power n dx is equal to x to the power n plus 1 over n plus 1 plus what? C. But because we have boundary values v1 and v2, we'll not be including c because the effect will eventually do what? Cancel out. So what do? We apply this here. We'll be having work is equal to c into v to the power minus n plus 1 over minus n plus 1. Then we'll have v2 v1. Now, this is the same thing. C into v to the power 1 minus n over 1 minus n v2 v1. So we can bring 1 minus n out. So we're having work is equal to c over 1 minus n into v to the power 1 minus n v1 v2. From indices, we know that v to the power 1 minus n is equal to v to the power 1 over v to the power n, and that is the same thing as v over v to the power n. So what do? We substitute v to the power 1 minus n with v over v to the power n. So we have any work equal to c over 1 minus n into v over v to the power n v1 v2. So the next thing would be to substitute v with the boundary values. We'll be having c over 1 minus n into v2 over v2 to the power n minus v1 over v1 to the power n. Now that gives us c v2 over 1 minus n into v2 to the power n minus c v1 over 1 minus n into v1 to the power n. But remember that p is equal to c over v to the power n, which implies that p1 is equal to c over v1 to the power n, and p2 is equal to c over v2 to the power n. So we come here, we are having c over v2 to the power n into v2 over 1 minus n, then minus c over v1 to the power n into v1 over 1 minus what? N. So this is what? P2 into what? v2 over 1 minus n minus p1 v1 over 1 minus n. When we're having common denominators, we're having p2 v2 minus p1 v1 over 1 minus n. So for a polytropic process, work is equal to P2V2 minus P1V1 over 1 minus n. So you'll be given n before you'll be able to calculate the value of work done. The next special case we are looking at is the case where V1 is equal to V2. So in other words, there is no change in volume. It's called isochoric process. Change in V is equal to 0 because V1 is equal to V2. Then what happens? Work will be equal to 0. Let's come back to the formula for polytropic process. Now, work is equal to P2V2 minus P1V1 over 1 minus n. Now, at this point, it will not be obvious because by the time we say V1 is equal to V2, it seems like we'll be getting a value for work. But let's go back to where we got this from. Now, that is C over 1 minus N into V2 over V2 to the power N minus V1 over V1 to the power N. Remember that C here is a constant, so it does not change. N also is a constant, that's the index. So we are having V2 over V2 to the power N minus V1 over V1 to the power N. Now, in a case or situation where V1 is equal to V2, we'll be having C over 1 minus N into V1 over V1 to the power N minus V1 over V1 to the power N, or C over 1 minus N into V2 over V2 to the power N minus V2 over V2 to the power N. Now, this will give us 0. This will also give us what? 0. 0 times C over 1 minus N will still be 0. The same thing applies what? Here. I forgot to tell you something. For the polytropic process, N is not equal to what? 1. N can be any number except 1. N can be 0, N can be 2, N can be any number, but not what? 1. Whereas in the isochronic process, V1 is equal to V2, implying that there is no change in volume, and as a result, work is equal to what? 0. So the third case we'll be looking at is where pressure is constant or fixed, and we'll call it isobaric process. Change in P is equal to 0, and that means P1 is equal to P2, or P is constant, that's P is equal to C. So for P to be equal to C, N must be equal to 0. Remember that PV to the power N is equal to C. For you to have P times 1 equal to C, that means V to the power 0 is equal to what? 1. So it's only when N is 0 that we can have V to the power 0 is equal to what? 1. So for isobaric process, P1 is equal to P2, that is change in P is equal to 0. Then P is equal to C, that's P is constant, and N is equal to 0. Now let's come back to the polytropic process formula. P2V2 minus P1V1 over 1 minus N. Applying this here, we'll be having P2V2 minus P1V1 over 1 minus 0. That gives us P2V2 minus P1V1 over 1. And that gives us P2V2 minus P1V1. But remember that P2 is equal to P1, and let's call it what? P, since pressure did not what? Change. So in that case, we'll be having PV2 minus PV1. Now, factorizing, we'll be having P into P minus V1. So when pressure is constant, work is equal to P into V2 minus V1. So the last case we'll be considering is the case where temperature is constant, and it's called isothermal process. Change in T is equal to 0, that's T2 is equal to what? T1. And for that to be true, N is equal to what? 1. Remember, in ideal gas equation, nRT is equal to PV, or mRT is equal to what? PV. Now this guy is fixed, or this guy is fixed, whichever one. Remember, the definition says for a fixed mass of gas. So when you're stating Boyle's law, Charles' law, you get, it's talking about a fixed mass of gas. In other words, mass is constant. And this is the gas constant, which is also what? Fixed. So for PV to be constant, T must also be what? Constant. If T is not constant, then PV is not constant. So when T is constant, it means that mRT is equal to constant, which is equal to what? PV. And remember, for the polytropic process, PV to the power N is equal to C. So if this is equal to this, it implies that N is equal to what? 1. So applying this here, we'll be having P2V2 minus P1V1 over 1 minus 1. That gives us P2V2 minus P1V1 over 0. This answer is undefined. So what do? We go back to the formula for work, and from there we derive the formula for isothermal process. Now we are having PV to the power n equal to C. But n is equal to 1, it implies that PV is equal to C. So pressure is equal to C over what? V. We come to this formula, we substitute for what? Pressure. So work is equal to integral V1 V2 C over V dV. Now we can bring out our C. C integral V1 V2 1 over V dV. Now integral of 1 over x dx is ln x. So in that case, we are having C into ln V, V1, V2. So what do we do? Substitute for V. That means you will use V2 and also use what? V1. So work is equal to C into ln V2 minus ln what? V1. Now from logarithm, we know that log x minus log C is equal to log x over C. So the same thing applies here. We're having work is equal to C ln V2 over what? V1. So minus here is the reason for this division sign. Assuming it's plus, we'll be doing what? Multiplication. So if you're asked to calculate work for an isothermal process, what you just need to do is to say work is equal to C ln V2 over V1. Now, the question is, what is C? We'll go back to our formula. PV is equal to C. So in that case, we are having PV ln V2 over V1. Now, this PV here simply means P1 V1, which is equal to P2 over V2. So we are having P1 V1 ln V2 over V1, which is equal to P2 V2 ln V2 over V1. So even if you use P1 V1 or use P2 V2, as long as you have ln V2 over V1, then that gives you the value per remote work. So P1 V1 ln V2 over V1 or P2 V2 ln V2 over V1 is equal to work done, whether by a system or on a system of an isothermal process. So what happens when you have a system containing an ideal gas and pressure is not given, but temperature is given? What do? You say PV is equal to mRT. This is the formula for what? Ideal gas. Then you have PV here. Substitute for PV, you'll be having mRT ln V2 over what? V1. So this is your temperature. Remember that temperature is not zero. Instead, change in temperature is equal to what? Zero. So if T2 is equal to T1, we can say it's equal to what? T. So whether it's the temperature of the second state or first state, it's still the same value. You insert it here, you have your R, you have your M, that's the mass of the gas, ln V2 over V1. That gives you the work for a system containing ideal gas when temperature is constant. The next thing is heat. This is energy transfer that occurs because of a temperature difference between a system and its surroundings. So what this implies is that when there's no temperature difference, there can't be what? Heat transfer. So the energy transfer that occurs because of a temperature difference between a system and its surroundings. So note, heat is not a property, just as work is not a property. Thus, the value depends on the details of a process and not just the end states. I've said that before. Unlike work, heat transfer to the system is positive. I said for work done on the system is negative. But for heat transferred to the system is positive. Whereas heat transferred from the system is negative. So work done by the system is positive, but heat transferred from the system is negative. Then work done on the system is negative, but heat transferred to the system is what? Positive. The symbol for heat in thermodynamics is Q. A process involving no heat transfer is called an adiabatic process. So a process that does not involve the transfer of heat, either from the system to the surroundings or from the surroundings to the system, is called an adiabatic process. We have three modes of heat transfer. The first one is conduction. So this is a mode of heat transfer that involves body contact. So the two bodies must be together for heat to be transferred. Now we have another mode of heat transfer, which is convection. So in this case, the two bodies are not in contact, but there is something transferring the heat from one body to the what? To the other. So it could be a gas, it could be a liquid. Take for instance, when hot air is coming to you, that is what? Heat coming to you, but through what? Through a medium, that's air. Now, the next mode of heat transfer is radiation. So in this case, we don't need liquid, we don't need gas. What we need is what? Electromagnetic wave. Energy is transferred from the system to the surroundings or from the surroundings to the system through electromagnetic waves. That leads us to the last thing, the first law of thermodynamics. So we looked at the zeroth law in my previous video, and in this video, we are looking at the first law of thermodynamics. It states that energy cannot be created nor destroyed. It can only change from one form to another or be transferred between a system and its surroundings. So in other words, energy is conserved. So what that means is when you have a system and you have the surroundings, there is no way you can be looking for what? A particular amount of energy. You get? So it must be either in the system or in the surroundings. So energy will change from one form to another, but cannot be destroyed or cannot be what? Created. Finally, we are looking at the energy balance equation for a closed system. So here we're having a system that moved from state 1 to state 2. So E1, K E1, P E1, U1. E1 is the total energy in the system at state 1. E2, the total energy in the system at state 2. KE1, the kinetic energy of the system at state 1. KE2, the kinetic energy of the system at state 2. PE1, the potential energy of the system at state 1. PE2, the potential energy of the system at state 2. U1, internal energy of the system at state 1. U2, the internal energy of the system at state 2. Now you notice that I did not write Q and W under the states. Instead, I wrote it in between to show you that these are part functions. So they don't depend on the states, rather they depend on the what? On the process. So here we have Q and W, that's means of transfer of energy. Now for the equation we're having change in E. Now I say change in E is E2 minus E1, change in KE, KE2 minus KE1, change in PE, PE2 minus PE1, and change in U, U2 minus U1. So change in E is the change in the total energy of the system. It does not mean the energy at state 2. Please take notes. It's talking about the difference in both what? Energies. So that means if we want to get the energy at state 2, E2 would be E1 plus change in what? E. That will give us our what? E2. So change in E is the change in the total energy of the system. It will be positive if the energy of the system increased, but negative if the energy of the system decreased. So this is equal to change in U, that's internal energy, plus change in KE, plus change in PE. And this is also equal to what? Q minus W, because these are the means of energy transfer. So we have Q and we have W. Now Q here means energy transfer to the system by heat. That's the net amount of energy transferred to the system by heat. But W here means the net amount of work done by the system. So if energy is transferred to the system, Q will be positive. If work is done by the system, W will be what? Positive. But if work is done on the system, that means the W will have a negative what? Value. And if energy is transferred from the system to the surroundings, that means Q will have a negative what? Value. So that's it. Q minus W gives us this. So it implies that E1 is equal to U1 plus KE1 plus PE1, and E2 is equal to U2 plus KE2 plus what? PE2. Now, I want to look at the rate of transfer of energy. The rate of transfer of energy. We'll be having the EDT is equal to the UDT plus the PEDT plus the KEDT, which is equal to Q dot. There is a dot here showing what? Rate of energy transfer by heat. Then minus W dot, rate of energy transfer by work. So this is the energy balance equation for a closed system, whereas this has to do with rate of energy transfer. So we can say change in E is equal to Q minus W, whereas the EDT, that's rate of energy transfer, is equal to Q dot minus W dot. So with this, we've come to the end of this video. I believe you've learned a lot. Please do well to like, do well to comment, share, and subscribe. Please share. I believe my video helps so many students who are finding it difficult to understand thermodynamics. So please help me share. I want to reach more students. Thank you so much for watching. God bless you. Don't forget to subscribe.